What is going on, guys? Let me, as usual, make sure that my stream's good. Let's see here. I think I need to turn the music down a little bit. It's a little too loud. Okay, that's better. Okay, I don't hear anything. Oh, something. That's what is going on, guys? Okay. Alright, everything's good. Make sure. What is going on, guys? Okay. Alright. Anywho. Alright, yeah, so today we're gonna be taking a look at stack canaries. For those of you who don't know, stack canaries are a mitigation put on binaries in order to keep people from overflowing the stack and taking over the instruction pointer. So like I said in the description, I already figured out how to leak the stack canary and I worked around it. I'm facing a completely different issue now, but right now for just a minute here, I'm gonna go through, explain what a stack canary is, where it's usually found, at least in 32-bit architecture, as well as what you need to work around it. And yeah, then we'll go from there. I'll finish up this challenge, hopefully, work around the current issue I'm facing, and that'll be that. So let's get into it. Alright, so first, first let me just fire this up. Okay. So depending on the debugger, decompiler, whatever thing you use, and actually, now that I mentioned that, let's fire a binary ninja too. Make this tabbed. Okay. Alright, so if we break on main and we run it, one of the first things you'll see, depending on how the binary was built, is you'll see this instruction right here, move GS. That's just another register, general purpose register in most modern CPUs now. GS hex 14, the value of GS hex 14 into EAX. Just to do that instruction, I had to pop my back. So this right here is the stack canary, right? At the beginning of each function with a binary that has stack canaries enabled, in each function, the stack frame will have a canary, right? So essentially what this does is, if there is a possibility for an overflow, and usually the compiler, I think, will detect that. That's my current theory, is it'll detect it, and so let's go over to Binary Ninja to show you exactly what I'm talking about, right? Okay. So main function with stack canaries enabled. You'll see, where is it? for the buffer that got declared. Okay, here it is. So this buffer got declared with hex 8c worth of space, right? If we pull up a calculator right here, 8c, that's 140 bytes of space since it's a character buffer. And then you'll see the vulnerability, which is right here, is at this call to read. This reads in at the beginning of buffer, the address of buffer, hex cc bytes. So hex cc is 204 bytes. So that is where we're going to overflow the stack. You'll see here that it reads up to hex 8c if you want to create a tweet, and 8d right here. This just resets the buffer. And my current theory is that the compiler will automatically detect where there could be possible buffer overflows. And I say this because whenever I was working on this and I was making my workaround, the stat canary comes right after the end of this buffer. That may just be chance. I don't have enough experience to tell you whether that is always the case, and it honestly could also be dependent on the compiler being used. It could be implemented differently, but that's just my current theory. So the stat canary is meant to keep people from detecting buffer overflows, and let me show you how it does that, right? So as I said before, when I was working on this, I found out that the stat canary, so it's not located exactly right after the edge of the buffer. More so, it's if you do overflow the stack. Okay, maybe it'll be better if I just show you what I mean. Okay, so let's get some input into this, right? Let's call. Now it'll make a call to scanf. Let's give it some random input. I know this is going to be more than 204 characters. That's fine. So see, it cuts off. Wait. Oh, I didn't put the number first. That's why. Okay. So let's create a tweet. Okay. Weird. I don't know why I did that. Okay, this is where we put our input. This will be over 204 bytes. Honestly, actually, we should have just did number 3, because that's where the vulnerability actually is. But we can just do that as well. Choice 3 to update the tweet. You can already see that we have A's on the this one as the arguments. Okay, now this will overflow the buffer. Now we give it our input. going on? That was weird. Okay, let's try that again. Okay. So, if we examine the stack right now, we can see our input right here, which overflowed the buffer. It's right here actually. And then this is the stat canary right here, right? How do I know that? Because typically the stat canary will have in this specific segment in the stack, it'll usually be no bytes, and then the first thing on the stack at that memory address will be the stat canary. So in order, it would be the stat canary, no bytes, and then whatever else is in memory. Now, if we step on printf, guess the length of our string. Okay, and then it'll prompt us for options again. And then we can exit. So once again, let's check the stack. Stack canary's in the same place for now. Move EAX. What is that EAX right now? Hex A into EPP minus hex A4. Let's examine that. It's going to compare it to, I'm guessing this is just comparing the, well, hex A is a new line character, I think. Jump equal, compare 0, what's that hex? EPP minus hex A0. B5. What's B5? I don't think it's an ASCII character. Yeah, it's not an ASCII character. Okay, that's our choice we made right there. That's the number we gave it. X, x4, jump equal. Okay, that was the if. Hex C from the stack pointer, so it's adding to the stack. Push whatever's at that address onto the stack. That's the string. Thanks for using tweet. Okay, now it's going to exit out of the function. So we're subtracting from the stack, we're tearing down the stack frame. Add hex 10, move, and then this right here, this is where the stat canary is located at. So now if we examine that location, we notice that it's all A's, right? When we look at the stack, we can see that it's taking the location it would expect to be overflowed at. And here in a second, you'll see it'll compare it with the location in which the stack canary is actually located, right? I mean, we can see in the next instruction. So to move that into EDX, so that's all A's, and then the location we saw before at the beginning of the program where it put the stat canary, GS hex 14, subtract whatever is there from EDX, and we don't get 0. So now it's going to, the 0 flag is set, or the 0 flag isn't set, and the call to jump equal is going to go to stack check fail. And there you go. So that's how stack canaries prevent buffer overflows. Okay. And then once it does that, it's going to print out stack smashing detected. And it'll kill the program before the overflow can actually do anything. So countering it, it's depending, like I said, depending on the way the program is built, can be either pretty simple or pretty difficult. I didn't have too many troubles with this. We can see here. So first, when I mentioned that the stack canary, let's go back into let's. So one thing, right? The stack canary will always have null bits. Or actually, I don't know if it'll always have null bits. That's just my experience so far. But in this case, whenever a string is being read into a buffer, in this specific scenario, I think what the compiler does is it'll append null bytes at the end for A, to prevent being leaked. So like I said before, we have to leak it in order to bypass it. And so we have to see how we can leak the address, right? So if you look at the stack again, so stack canary is right here. And remember, the input goes it goes from lower addresses to higher addresses, right? So whenever we're overflowing the stack, it'll go in this direction here, from right to left. So from right to left, right to left, right to left, all the way down to the stack canary, and we can see here that the first bytes in the stack canary that will be affected are the null bytes. Okay, so if you look at the decompilation of the program right here, we can look at what this program does, and we see that here, whenever you create a tweet, because the stack canary gets compared with the first byte after the limit, after the edge, it appends a new line at the last position, which is what we need. Because null bytes are right here. And there's no other way to leak it except by executing one of these branches, particularly this one where we update the tweet, so that we can then leak the stack canary, right? And I already made a program here, so I figured out where that was. And then whenever it leaks the address, I take the canary, and that's pretty much that. So, trying to think here. Is there anything else I missed? No, I think I pretty much hit on everything. So that's yeah, that's how you like I said, depending on the binary that you have, there's different ways to leak it. But in my specific case, I see that the only option for me in order to leak it is to um, put in the max amount of input that this call will take, and then at the end it appends a new line which will leak the address. Now I'm thinking about it now, and it's actually, I'm kind of confused because we saw before that it didn't actually overwrite the stack canary, right? We can look for this in our stack. See if we find it. DE9A. Yeah. So it doesn't actually leak it the way I think it did. Yeah, because if we could overwrite the stat canary where the compiler decided to put it, it'd be pretty useless, because then it would just compare whatever's here, whatever we overwritten it with, and we would be able to bypass it that way. But we're able to leak the address regardless. So let's step through again and see how exactly that happens. Do 3 read, give it this much input. We'll examine this stack again. So, like I said before, the stack canary is right there. This is the max input we can give it. And it compares whatever's the last the first byte past this boundary right here. It compares that to the stack canary at the end. Yet whenever we add a new line right there, we can see that the canary gets leaked. And actually, let me restart it, and actually, how about this? I'll show you. Okay. Alright, yeah, let's run this script attached to it. Except it won't. So currently I'm using Pwn Tools and GDB, the module attaching to this program. It doesn't work for some reason, so I have to do it externally. And so it already executes all of this by the time we get it. I guess what I could do is just comment out everything. Yeah, yeah, let's do that. And we'll print that. And then we'll go ahead. Oh yeah. And activate. We will execute it. Okay, so alright. We can see here that at the new line, it leaks the address. So hex 03 X hex F6, so whatever the ASCII for hex or X is. ABCD, make sure X was 78, so 03, 78, F6, and then this would be 03 or 00. So we can go in and attach and confirm that it's the actual canary that got leaked. And then we can provide the next option here just so it doesn't rush through the program. Go through all these calls. Right here. Same the stack. So we said, what was it again? 03. Or is it? Oh no, right here. Okay. So that's the new line right there, and the address gets leaked right here. But it's weird because I mean, we have so much junk between there and the stack canary. So I'm not entirely sure how it got leaked exactly. Let me check. Lining 0A. Right, that's right here. Okay. Oh, I was wrong. So it goes from the least significant portion here all the way up here, and then to the next slot, and to the next slot, and so on and so forth. So this is the new line. This is whatever character that was there. I think it was a B, maybe? I don't know. And then it appends a new line here, and we get the memory address leaked. Interesting stuff. Because I'm not entirely sure why, when we checked before, the address wasn't there. Let's check again. Let's check again. And this time we won't overflow the stack or give like the max input. We're just gonna give a couple characters worth. Per tweet, break main, run. Give it 3. Let's call. Give it that. Okay, so let's examine the stack again. Here's our input. Where's this canary? It's right there. Oh. No. That's right. Yeah, we see it right here. Okay. So it does keep the value at the address. Um, let's count the bytes, right? So this is 1, 2, 3, 4, 4 each, 4, 8, 12, 16, 32, 36, 40, 44, 48, 52, 56, 60, 64, 68, 72, 76, 80, 16 times 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9 minus 12. So 16 times 9 minus 12. It's 144. Yep. See. So, minus 4, actually. Because it is still going, it's going left to right. Oh, yeah. So this, we would exclude this. This is 4 bytes right here, and these get filled. Okay, so... Alright, so that was my bad. We do have the stack canary put at the address at the end of the buffer, like the edge of the buffer, the address or the byte that would overflow, start the overflow. And yeah, so that's how we leak the memory address. So can confirm that now, we're good. However, now the issue that I'm running into is after I overflow the buffer, I'm not able to get control over the instruction pointer, right? So I'm gonna try something because I may have miscalculated how much exactly I was supposed to give it. So what we're going to do is we're going to comment this out and this. We're going to test something. And I think I already tested this yesterday. Yeah, I did, because I have the pattern right here. Input the canary reversed. And then the secondary pattern. So we have 140. And then we can overwrite 140. The buffer is 140 bytes wide. We have 204 bytes. So 200. 4 minus 140. That's 64 bytes. Let's see what happens when we generate a pattern like that. 64. NOP. So it'll take up to NOP. It'll take up to here. And then I gave it extra because I was confused why I wasn't getting control over the instruction pointer. So let's test this again, shall we? See, if we give it pass, it'll give us invalid input. Let's attach to it and see what's going on exactly. Gosh, I have to give it input. Okay. So we have our initial pattern right here, stack canary right there, and then the overflow we've given it. It could be that we just need to make another call, like a different, instead of exiting, like trying to exit, we could I guess try calling, like, what was it again? Try calling 2 to reset it, see if that gets us control over the instruction pointer, or we can try calling 1. But either way, I'll show you guys what I mean exactly when I say I don't have control over the instruction pointer. Push, puts, so that's that, move 0 into EX. This moves the stack canary to subtract at 0, so that's good. Move whatever's there into ECX. That destroys the stack frame right there. Load effective address of, and see it's unmapped, so it's ECX. But let me go over to my notes. Counter registries, shifting strings. Base of the stack, yeah. I mean, there's a couple ways we could go about it, I guess. We could use the base pointer and the stack pointer to generate our own stack frame. But again, we still don't have control over the instruction pointer. So then whenever this will try to return, it'll return to whatever is at first I thought if I just overwrote the base pointer that would work, but another problem is that it moves whatever's in ECX over to ESP and it subtracts from it. So we could try giving it a valid address and see if that works. And I tried doing that here, except I didn't account for the BAA portion. I just want to test the theory real quick. So -4, so we need to add 4 to that, maybe. X first forward to ECX. What effect matters? Oh, okay. Minus X for, okay, so we need to make that 74. Test 32. Do test plus refine. See if that does anything. Okay, let's see. Move that into EDX. Yeah. Leave what effective address. And return. Okay, yeah, see. Cannot access memory at address hex 14A1. And if we had, I mean, besides the fact that the stack is non-executable, 14A1. I'm not sure where it got 1481 from. Let's try running it again. Look closely at what it's doing, so I can understand what's going on exactly. That's our choice. It's calling you. Thanks for using tweet, whatever. Adding to the stack hex 10. So we should be at 90. That's our choice right there again. Yeah. Move the stack canary. Now it's exiting the program. We have default pointer, base pointer. Minus hex 4. That's the thing we put there. Okay. Load the address at whatever it is at ECX minus hex 4, which would be the beginning of that function, into the stack pointer, the ret, and it returns to 14A1. That's the instruction it points to then. Let's look at the base pointer again, I guess. Oh, okay. So, okay, so it returns like we expect it to. The base pointer is held for it holds the return address whenever you call ret. Cannot access memory at 14A1. Why is that? Read flag plus 4. Let's see. 9270. Let's see what the beginning of the function is. Could be that I was just doing it wrong. Okay, so we know that it ends in 70. Now where is read flag? Oh, okay. That's interesting. C. So maybe another situation where 80492.270. Could be that it's because of address randomization. That's my first bet. This isn't a position independent executable, so that's interesting. 49270. Trying to find that address. 9216 print banner. 926C. I mean, we could give it the address, but I know for a fact that I gave it. I looked at this before and I gave it that address yesterday specifically. Let's try that. So, okay, so it's most definitely ASLR because regardless of whether the binary is a position independent executable or not, ASLR will still randomize the binaries that get loaded into it. However, the fact that it's not PIE, it shouldn't be randomizing the binary itself, like where it gets loaded. And I guess I can look this up. ASLR still randomize where the binary gets loaded. How's it going, man? Welcome to the program. I'm sorry. I thought the show was over. It started? Yeah. Oh, yeah. Okay, well, I guess we can test our theory. Let's just try, let's disable SLR first, and then we will find the function. Ugh, come on, man. Goodness. We have 4926C, which was the same address we just saw. Okay. I guess let's change that address. 926C. If we add 4DE, was an us issue. Oh yeah, because I tried that yesterday. So it's not AOSLR. It's affecting binary. Okay, so like I suspected. So if we examine it again, yeah, same thing, 6C. So let's try it. Stack canary. Send 0. It's 4 instructions. Effective address. 4. That's the first instruction. Okay. So then if we examine base pointer again, so the first thing it points to is that, and it can't access the memory there. Okay. So it's not that I was doing it wrong necessarily, it's just it won't execute past that point. And it can't access memory at that address because I believe these are instructions, it's not data. I think. Yeah. Okay. So then all we gotta do is find what to call so that we can have control over the instruction pointer. So let's test our stuff out again. So instead of calling, we call 3, and then we will actually, let's keep it interactive. Let's make different calls and see what happens. Attach to it. Let's I guess let's try 2. if statement now. Subtract from the stack. Push 8D. I think it's about to UP. Push EX. It's about to reset the memory. See, but if we examine the stack, all they got reset, interestingly enough. So that doesn't affect our execution regardless. Just trying to see what we can do to get control over the instruction pointer. Jump. We can try exiting now. Same thing. I guess now we can try just create a tweet again. wonder if where did our input go? Okay. Don't know why I did that. So I added an extra new line. Okay. EA, BP, and EAX. Oh, okay, I see. That's just the new. Okay, well, I guess here's a potential attack vector because it's well, it's not adding anything new. It's not pushing into it. It's just overriding it. But it's also adding a new line at the end. EAX. Push. Retweet. Printf. So okay, that's just overriding. It's not pushing anything new. Add 10 to the stack. Subtract that much from the stack pointer. Push. Okay, now it's gonna prompt us for options again. Let's try 3 this time, I guess. Yeah, sure. Just gonna get an empty input. And 10 in the stack. EX and a DMR pointer. 0 into EBP plus EAX times 1 minus hex 98. So it's appending the null byte. Hmm. Guess we can try exiting now. Hmm. Okay, so none of what we did gave us control over the instruction pointer. Hmm. Hmm. And then XEX says return 0. Return 0. The only two values are EDX and EAX. EAX is typically what returns. Yeah, stores the return values. Hmm. Well, meta stump. I'm stumped right now. Not really sure what I can do now. bytes did we get overflow? Total 64 bytes extra. We know that it was only 64 bytes because we tried to put in more. They wouldn't let us. Might have to get creative because I'm wondering. Let's put a base pointer, a stack pointer. I think that might be what we have to do is set up a stack frame. Give it the return address. Because when it does leave, it destroys the stack frame. You can try it. Ooh, this is a hard one. This is indeed a hard one because I mean, whenever the ret instruction, let's run it again and pay closer attention to what happens exactly, because like I was saying, the ret instruction based on the C decal, I believe, pushing the return value onto the stack. No, it's EAX. Holds the return value into EAX. And we only have control over ECX, ESP, the stack pointer, and the base pointer. Try to get a little more insight. Jump ECX. Transfers program control to a return address located on top of the stack. It's a stack by call instruction, and the return is made. Instruction that follows the call instruction. Okay. Let's see. Don't have control over this instruction pointer. So then the only option we have is to see what gets placed on the stack at the time of ret. So let's see. I gotta see how much is taken off that stack. 6. And then ret. Huh. Then we'll redo that. Whenever we do that, it won't let us do that. So let's keep paying closer attention to what's going on with the stack. Force, trapped, push, call, 0, EDX, So we're now FFE 52240. 52240 and then EC, so it adds quite a bit to the stack. And then it's so it has to be something on the stack. The return address of if we can find the return address or something on the stack, then we'd be able to do this. We need something that points to the function. Okay, let's try it again. We'll check the stack. Hmm. 605 CEC83, that's the first instruction. this. Ah, here we go. Start. Nothing. Keyboard pointer. 20. And CC. See, there's an address right there and it points to the function. Create some we need to either find something that points to read flag or find some other way to do it, like point it back to start or something. I don't know. Oh, wait. Hold up. Might be cooking here. Because we noticed that our function was on the stack. We just need to figure out where the stack it is and point it. Pointer right here, 9270. If we can point it, so it's at 10, 11. Because it loads set ECX -4. Let's keep going through this. Base pointer -4 into ECX. Let's read flag. Ooh, okay. And then when it leaves, then it'll pop that into the stack and return. So if we do we can overwrite the A's in here with the stack address. But the problem is it's going to be different each time, maybe. This is complicated. just remember this. FFB 7820. FFB 7820. Oh, we might be in luck actually. No. It'll always start with FF. That's what's allocated for the stack, or that's what it'll never be consistent. Maybe I'm missing something. I don't know. No, I gotta overflow the stack, or to overwrite something. And I mean the instruction, I can't overwrite the instruction pointer, so I don't know. Can't do anything related to the stack. So change the addresses each time. Maybe we can try using that, because that can be accessed, and maybe the instruction pointer will continue from there. it, I guess. Huh. That's interesting. As long as it points to something, you can do it. That's cool. Hmm. That's the thing, is we can't even manipulate the return address. Okay, well. I think I'm gonna have to end it there. Yeah, I'm gonna end it there. So yeah, that was Stat Canaries, how to bypass them, and then, you know, possible struggles that you have after. I definitely gotta look at this more, because I know there's something I'm missing, I just don't know what. So, anywho, hope y'all enjoyed this. Hopefully it's useful information for y'all, and I will see you at a later time.